Number 55. A large electrical power station generates 1,000 megawatts of electricity with an efficiency of 35%. Letter A. Calculate the heat transfer to the power station Q sub H in 1 day. All right. So basically they're talking about efficiency. They're talking about an energy, which is basically a work in this case. Well, this is really power. So, but we will convert that into energy basically. And they're asking us for Q sub H. So I know I'm probably going to be using this formula over here on the right-hand side. It says that the efficiency, all right, I'll just label it E, is going to be equal to the work divided by the temperature. Excuse me, not the temperature, but the heat donated basically to the hot reservoir, or in this case, this is going to represent the heat transferred into the power station, and this will represent the electrical power that the electrical energy that the power station is generating. But they told us a value in megawatts, right? So we know that that's power. And watch, megawatt, erase the watt, and you know a watt is a joule per second. So this is really 1,000 megajoules per second. And we have to somehow take this value and convert it into joules. Well, the question is, well, how do you get rid of seconds? Well, that's why they told you the 1 day part, right? If this is the amount of megajoules that's generated every second, how much is generated over a day? Well, that's easy to find out, right? We just have to do some conversions. Let's first get rid of megajoules. So we can put megajoule on the bottom, joule on the top. There's 10 to the 6 joules in 1 megajoule, so that's great. That cancels. Then simply now, we have to get rid of seconds. So seconds on the top, we can go to hours, right? 3,600 seconds in 1 hour. And then get rid of hours and go to days, that there's 24 hours in 1 day. And lo and behold, now we'll have our value. So this is going to be 1,000 times 10 raised to the 6th, times then 3,600, times then 24. So this works out to be about 8.63 times 10 raised to the 13th joules, right? This is now joules per day. And that's fine, but they wanted me to find the heat energy per day, right? That's transferred to the station. So essentially, when I look at this formula, I can say that the efficiency will be equal to the amount of work done per day divided by the heat transferred to the power station per day. Now, I just found the heat transferred per day, and if I plug that in with my efficiency now, right off, if I said that this is the amount of heat energy, I am incorrect. This is the work done by the power station, as it tells us that. All right, this is the amount of work done by the power station per day. So if I plug that in for work and the efficiency, then I will find the heat energy donated or transferred to the power station per day. So hopefully that makes sense. So we're just going to say that the Q, right, the heat energy transferred to the station per day, will equal then the work done by that power station per day divided by the efficiency. So here we go. Work is going to be, we just calculated 8.63 times 10 to the 13th, divided then by the efficiency of 0.35. You need that in decimal form. And here we find Q sub H, right? This is sub H. And this is per day again. Hopefully that makes sense. So divide that by 0.35. And here we come up with a value of approximately 2.47 times 10 raised to the 14th joules. And that's, again, remember, this is all per day. All right. So that's the answer to part A. I'll leave that over here. All right. And I'm going to get rid of some of this work so I have a little more space. How you guys doing today? All right. Well, maybe you might have, I asked that question a couple problems ago. You might be saying, well, it's still the same day, Andrew. I've been working on 17 of your problems. So if it's just later in the day, I hope you had a good day. If it's a different day, I hope today's going well for you. Anyway, let's take a look at now letter B. So letter B. How much heat transfer Q sub C occurs to the environment in 1 day? Okay, so we just have to now, we know Q sub H, we knew the work before, right? We calculated that, that's right here. So now we have to relate it to Q sub C. That's probably this formula over here, right? That the work is equal to the heat transferred, right? Hot minus then the cold. Okay, so this represents the amount of heat. This represents essentially in this problem the amount of heat transferred to the power station, and then this represents the amount of heat lost to the environment. So now I got to find Q sub C, right? So simply just algebraically manipulate this. So Q sub C will equal Q sub H minus then the work. So Q sub C will then equal the 2.47 that we just found times 10 to the 14th minus then the work of 8.63 times 10 to the 13th that we found before. And lo and behold, this works out to be a simple calculation. So minus 8.63 times 10 to the 13th. And there's going to be about 1.61. 1.61 times 10 raised to the 14th. And that's in terms of joules again. Okay, this is per day. All of this stuff is basically per day. All right, so that's the amount of heat lost to the environment per day. All right, so let's take a look at letter C. So if the heat transfer in the cooling towers is from 35 degrees Celsius water into the local air mass, which increases in temperature from 18 degrees Celsius to 20 degrees Celsius, what is the total increase in entropy due to this heat transfer? So whenever you're thinking about total increase in entropy, you have to take into account if there's one object we're talking about or a system with two objects, basically. And in this case, we're talking about basically a system of two objects. So the total entropy change will be basically, right, the entropy change for the water here, and then the entropy changed for the air. Okay? So what's losing energy? What's gaining energy? Well, if the heat is transferring from the water, right, doesn't that mean that this is probably losing energy, right? And if the air is heating up, doesn't this mean it's gaining? So basically I can say that the total entropy change for the whole system will be equal to the entropy change, right, for the item that is gaining the energy, all right, or gaining the entropy, I should say. And by gaining entropy, you're gaining energy, heat energy, that is. And this would be then, in this case, the air, minus then the thing that's losing the entropy or losing the heat energy. And in this case, that's going to be the water. Okay? So now, expanding on each of these two terms by using this equation over here on the right-hand side, we realize that the total entropy change is going to be equal to the heat energy gained, right, by the air, because the air was warming up, divided by the temperature of the air. Now you might say, well, wait a minute, they gave us two temperatures. Well, what I'm going to assume is I'm basically going to assume that the average time it took to get from 18 to 20 was equally distributed over this temperature range. And therefore, I can simply just take the average temperature. All right. Now minus, right, the heat energy lost, basically. Don't plug in a double negative here. I'm already taking that into account. All right. This is now for the water. I'll label that W, and this should basically be air. Divided them by the temperature of that water. And it sounds like we have everything we need, right? So the change in this was the amount that was lost to the environment, remember. I know this is like Q sub C, and now this we're talking about Q sub H or whatever. I could have left this just, what might have been a little more appropriate is just left this as actually just Q, all right? Q sub W, Q sub A. You can call Q sub C A if you wanted, Q sub C B, Q sub C W, it doesn't matter. So anyway, this is the amount of heat that's being lost, right, from the water and being gained then by the air. So this would be the value now, 1.61 times 10 to the 14th, divided now by the average temperature of the air. Now remember, you need this in terms of Kelvin, okay? However, though, finding the average, so we'll just find it in terms of Kelvin, right? So do 18 plus the 273, right, plus then the 20 plus the 273. All right, add those two then together. I know I'm not really writing it out, but I think this should be pretty easy at this point. Then divide it now. Divide it by 2. And what do you get? You get about 292, right? So 292. Well, 292 in Celsius is actually 19, right? So you could have just looked at this and said, well, the average between 18 and 20 is 19 degrees Celsius, and then converted that into Kelvin, which would have been 292, right? You're just going to add 273 to this. Okay, now that my brain is on fire, let's plug that on in. So this is 292 degrees Kelvin, or Kelvin, and then subtract now the temperature loss of the water, which is the same now, 1.61 times 10 to the 14th. Then all divided now by the temperature of that water, which is 35 degrees Celsius, but you know we need that in Kelvin. So take the 35 plus the 273, so that's 308. Okay? And now just simply plug it on into the calculator. So this is going to be 1.61 divided by, 1.61 times 10 to the, why don't I use the exact value, right? Let me go back 1 second. Guys, there we go. I'm going to use the exact value, 1.60557, whatever, times 10 to the 14th. Divide that by 292, and then subtract from that now that answer again, that exact value again. Oh, this is fun going back in the calculator. And then dividing it by 308. So what do we get? We get a total entropy change now of about 2.86 or so. 2.86 times 10 raised to the 10th. And that is in terms of joules per Kelvin. All right, that's what entropy is in. Those are the units. All right, so that would be about the total increase in entropy. And now, letter D, let me just move this on over to the side. So letter D now is going to be how much energy becomes unavailable due to work because of this increase in entropy, assuming that 18 is the lowest temperature. Now remember, I forgot the number, so I apologize, but one of the prior problems I had mentioned to memorize this formula, that the total change in entropy will equal the work that's unavailable, okay, divided then by the lowest temperature. So all we now need to do is basically just find this work unavailable, okay? And let me just make that a little U for unavailable. Just to find that, we just have to simply then multiply the change in entropy total by then the lowest temperature. And this, the work unavailable, then becomes, right, the total entropy change we just found is 2.86 times 10 to the 10th, multiplied by the lowest temperature. Remember, you need that in Kelvin. So that's 18 plus than the 273. And then lo and behold, the work unavailable will simply become, take that value, multiply it then by 18 plus the 273. And this is about 8.31 or so. 8.31 times 10 raised to the 12th. And that is in terms of joules. All right, so that's the energy, the work energy unavailable, basically. Guys, thank you so much for tuning in. Appreciate it very much. Please remember to help us out and subscribe. And we look forward to helping you with more problems in the future. Take care.